A priori knowledge is truth derived entirely independent of observation. We know that 1 plus 1 equals 2, not because we measured it, but through pure deductive logic. But as mathematics scales into deep theory, that strict logic produces dense, impenetrable equations. This creates a paradox at the highest levels of the field. In theory, advanced mathematical statements are completely deducible. In practice, the sheer volume of calculations required to prove them quickly outstrips the processing capacity of the human mind. When pure algebraic deduction fails, mathematicians often rely on what philosophers call the method of simulation. They use spatial, rational intuition to model a problem in the mind's eye. This is the story of how a 30-year mathematical deadlock was finally broken by abandoning strict algebraic calculation and inventing an entirely new geometric space to simulate the answer. Reaching absolute foundational truth sometimes requires leaving the domain of numbers behind entirely. This diagram represents two historically isolated fields of mathematics: number theory, the study of integers, and harmonic analysis, the study of periodic waves. In the late 1960s, a mathematician named Robert Langlands proposed a massive theoretical framework, the Langlands program, to connect them. The program outlined a theoretical bridge between these continents, but the mathematical proof required to complete the span contained a glaring gap. In 1979, Langlands formalized this missing piece. He proposed a highly technical matching conjecture to align the two fields, and casually named it the fundamental lemma. In mathematics, a lemma is typically a stepping stone, a minor proposition proved on the way to a larger theorem. Langlands and the wider community initially assumed this specific conjecture would yield to standard algebraic techniques. It was viewed as a minor irritant. But the equations did not yield. Year after year, attempts to prove dilemma collapsed under their own complexity, turning the minor irritant into a definitive roadblock. For 3 decades, the grand unification of modern mathematics was frozen in place because no one could cross this highly technical bridge. To understand the roadblock, we have to look at the mechanics of the lemma itself. It required proving precise combinatorial identities between local orbital integrals. Orbital integrals are mathematical functions used to calculate the volume of specific spaces. We can see how this operates conceptually using a visual model developed by mathematician William Castleman. Here, a central point branches outward into a sparse, symmetrical tree. The simplest case of dilemma relies on point-counting logic. It tallies points with alternating signs at various distances from the center, calculating values like 1, then 1 minus 3 equals -2, then 1 minus 3 plus 6 equals 4. But when this formula is applied to higher dimensions, the sequence loses its simplicity. The number of required calculations explodes, triggering an exponential combinatorial expansion. This combinatorial wall stalled the mathematical world. The sheer volume of point counting required to prove the identities across all dimensions could not be calculated by any human mind. The difficulty was so severe that Robert Langlands eventually abandoned the problem, turning his attention to other fields of research. Pure algebraic logic had reached a definitive dead end. Moving the science forward would require a distinct shift in perspective. That shift came from Ngo Bao Chao. Raised in a family of intellectuals in Hanoi, Vietnam, Ngo demonstrated a profound early aptitude for abstract logic, winning 2 gold medals at the International Mathematical Olympiad. He migrated to France to study at the École Normale Supérieure. There, under the supervision of Gérard Lomont, Ngo began to systematically dismantle the fundamental lemma. His initial attempts met the exact same combinatorial wall. For 3 years, Ngo tried to force his way through the algebraic density, leading to a period of deep academic despair. Realizing that the numerical pathways were closed, Ngo made a crucial decision. He abandoned the strict number-theoretic approach entirely and attempted to map the algebra onto a completely different mathematical domain, geometry. He reasoned that the only way to prove this discrete algebraic identity was to translate the numbers into a continuous shape, something he could physically manipulate in his mind. To house this new simulation, Ngo utilized a highly advanced geometric construct known as a Hitchin fibration. A Hitchin vibration is a complex mapping tool, originally developed to study vector bundles on algebraic curves. By projecting the math into this space, the static two-dimensional logical tree diagram transforms into a smoothly folding three-dimensional topological manifold. Go took the rigid orbital integrals from the number theory equation and mapped them directly onto the rational points of this new three-dimensional surface. The mechanical advantage of this geometry was that it allowed for deformations. Instead of counting infinite points one by one, Go could flex and bend the shapes as a whole to find structural equivalencies. He was using spatial simulation to intuitively see and prove the a priori truth that the dense algebra had obscured. The strategy worked. In 2008, by solving the geometry of this newly invented space, No definitively proved the fundamental lemma. By translating a rigid numerical problem into a space where smooth movement and deformation were possible, he bypassed the combinatorial explosion entirely. When No's geometric proof was officially confirmed to hold up under scrutiny, the reaction across the field was immediate. It triggered a theoretical domino effect. Dozens of major theorems that had assumed the lemma was true for decades were suddenly validated as absolute mathematical law. Most critically, the proof stabilized the Arthur-Selberg trace formula, the exact equation needed to bridge number theory and harmonic analysis, officially completing the Langlands unification. For this achievement, No was awarded the 2010 Fields Medal, the highest honor in mathematics, firmly establishing his legacy. His single 169-page proof upgraded a vast web of theoretical assumptions into established, unshakable fact. No's proof resolved a 30-year-old mathematical deadlock while simultaneously creating a new interface for theoretical physics. Today, theoretical physicists are actively using these exact abstract geometric structures, specifically Hitchin vibrations, to model the behavior of vibrating string theory and gauge fields, which brings us back to the nature of a priori knowledge. It is not always a process of passive deduction. Reaching the deepest levels of logic often requires profound, active structural imagination. Reason can deduce the structural patterns of our reality, provided we are willing to build the geometric architecture required to see them.